Okay, so yesterday we started kinematics, just a lot of language. We talked, if you are, did I post a video? I think I forgot to post my video yesterday. So if you were away yesterday and you tried to look at the video, I apologize. If you were away and did not look at the video, well, then you're fine. I will post it today after school. You have a chance to look at it this weekend. Lots of language. I introduced to you guys the concept of scalars and vectors. Some of you have heard them before, some of you had not. They are just mathematical constructs that we slide different physical concepts into. So a scalar was a quantity with only a magnitude. A vector was a quantity with both a magnitude and a direction. We gave some examples of those, and then we started talking about some specific examples of each. So position, where we start in kinematics is all about where you are. And then we start to move you. We talked about position, distance, and displacement. I was in the middle of an example. And then the bell went. We were talking about displacement, or distance and displacement. Distance we had defined yesterday as how far away something is, or how far you've traveled, like the actual ground you covered to get there. So in this example that I gave you here, Lachlan said, I think it was Lachlan, that our little stick person had traveled 10 meters because they went 6 out and came back 4, and distances only ever add. Raina, good afternoon. In Teams? Oh, there it is. Yes, you did. Drama teacher. Favorite childhood cartoon? Nice. And then we were going to talk about displacement at the bow ring. So let's talk about displacement of this dude here. What is the displacement for this individual? They went 6 out, they came 4 back. Displacement, remember, we defined as how far you moved from where you started, the straight line distance and direction from start to finish. It does not care about the path you took. The path you took is irrelevant. All it cares about is I was here, now I'm there, and this is how far it is and the direction it is from here to there. So this black line that we drew has nothing to do with displacement. This pink line I'm about to draw has everything to do with displacement. This is where our person was initially. This is where our person was finally. So what is the displacement of our person? 2 meters. That is an insufficient answer. It is correct, but it is incomplete. Displacement is to the right. Displacement is a vector. It needs a direction. So let's include it. 2 meters right. That's it. There it is. Another example I was going to give you, which I will give you now. Same stick person. If they go out and they come all the way back, which is something that we did talk about. I demonstrated this. They got 60 feet out. They came back 60 feet. This is literally what I did. What is the distance? And remember, distance is denoted by the letter D, no arrow. What is the distance traveled by our stick person? Yeah, distance is add. 60 out, 60 back is 120 feet total. 60 feet plus 60 feet is 120 feet. And the displacement, the letter D with the arrow, signifying that we're, oh, nope. Displacement is triangle and the D with the arrow. D with the arrow is position. Displacement is the change in position. That little triangle there means the change in. What's the change in position? 0. And there is no direction because there is no displacement. You can't give a direction if there has not been a change in position. Grushan, favorite childhood cartoon? Favorite childhood cartoon? Okay. I think so too.
Measure it.
Like actually though? You guys felt that too? Yeah, that was totally an earthquake. We just had an earthquake. No, you're good. Yeah, that was an earthquake. I'm pulling up the Canada I just told them not to. Okay, so according to the earthquake tracker, we just had a 4.8 magnitude earthquake.
Where?
Beneath Seashell. 27K down. 5. That's legit.
Did we measure that?
We did. It's been measured. Yeah, 4.8. Seashell's on the island, right? Like Victoria?
How many rulers have
Seashell? Oh, it's one of those. Oh yeah, you're totally right. It's, oh yeah, up from Gibson's. Yeah, 27 kilometers from Seashell. Wow. That was weird. Okay. Yeah, no, we definitely felt it. Okay, so yes, that was in fact an earthquake. That's weird. That's the second time I felt one at school. First, I was in grade 9, the first one, and the picture started bouncing off the walls. That's weird. Yeah, according to the U.S. Geological Survey, there was just an earthquake beneath Seashell. That was legit. Okay, if we can, let's pull it back. Let's bring it back. We all just survived an earthquake. Congratulations. The same kind of example. We've got car. We're now changing things. We've got a car on a number line. This is what we've called 0 on our number line. That is the origin as defined by the setup of the problem. And we've got two cars. We've got a car A and we've got car B. What is the distance between those two? It's going to be 9, because this one is 2 to the left of the origin, and this one's 7 to the right of the origin. So the distance between them, absolutely, that's going to be 9. And I think we're told, are we told? Measured in kilometers, so that's going to be 9K. You absolutely need to include units if they're provided. So the distance of car A from car B is going to be 9 kilometers. The distance of car B from car A, it only makes sense if those are the same value. 9 kilometers. Distance doesn't care which way you go. Sorry, what? That's my K. Oh yeah, now my wife and children are texting me about the earthquake. Okay, 9 kilometers. Yeah, that's a km, not a 1 over m or 1 over 1. So talking about position now, position is always relative to the origin. What's the position of car A? -2. Or another way to talk about the position of car 2 is to say what? Instead of writing it as negative, because this negative is just the direction, the magnitude is the same, but we could give the direction a different way. Instead of saying -2, we could say that car A is, it's not going to be right, it's going to be to the left. Lefts and rights are important. So -2 or 2 to the left, again, both of those are going to be in kilometers as well. Position's a vector, it needs a direction. Position of car B is where? There's 2 ways you could quote it. 7. Well, and if you're going to give the direction as that value, put in the plus sign, just so we're really clear. It's either going to be at +7 kilometers or it's going to be at 7 kilometers right. Well, and then to find the displacement, we said question D and E says, what is the displacement of car A measured from car B, and what is the displacement of car B measured from car A? If you recall, displacement change in position, is equal to the final minus the initial. So if we want the displacement of car A as measured from car B, actually I should put this in here, final position minus initial position. If I want the displacement of car A as measured from car B, then car B is going to be our initial position. Car A is going to be at its final position. So the final position here is going to be -2 minus the initial position. Car B is at 7, +7. So if we're going to formalize this with some mathematics, we'd say, okay, well, the final position is -2. The initial position is 7. -2 minus +7 is -9 kilometers, or 9 kilometers left of car B. So then the displacement of car B as measured from car A would be what? The displacement of car B as measured from car A would be what? We could do it the exact same way. I've given you a formalization, or the math behind it. Yeah, it's going to be 9, +9 this time, not negative. Because if the final position of car B is over here, the position is 7. And then we want to, okay, it's always final position minus initial position. The car B ends here at 7. We're going to take away whatever the initial position was. Well, the initial position is being measured from car A, and car A's position is -2. So what's 7 minus -2? 9, positive. So that's an equal sign in there, 9 kilometers to the right. So the distances are the same, the displacements are different, just because of that direction change. Another example to make things more interesting, let's break it out into multiple dimensions now. If I decide I'm thirsty and I want to go for a Slurpee and I'm going to walk to the nearest 7-Eleven, we have one kind of close by. In order to get there, I'm going to follow sidewalks because safety is cool. And we're going to assume, I'm going to simplify the journey a little bit. I'm going to say this is the front of the school. I'm going to walk Abbey Arts Center. I'm just going to follow, assume it's a straight path. And then I'm going to hit kind of by the townhouse complexy thing there. I'm going to turn to the right. And assuming that it's a straight shot, obviously we're jaywalking. We go this way. We go this way. We get our Slurpees. What's the distance traveled? Well, the path is what? What is the distance traveled by our person? I can slide this thing up. Who said that? Lachlan, was that you? Someone said 400 meters. 450 meters. We traveled 300 meters down this path. And again, I don't know if these distances are accurate. I'm ballparking them here. We traveled 3 meters this way. We traveled 150 meters this way. So our total distance traveled is 450 meters. Distance is all about the actual path you took to get to where you ended up. But then to figure out the displacement doesn't care about the path you took. Displacement just says I started here at Abbey and I ended here. And so what we want is the straight line distance and the direction from where we started to where we ended. So this purple line that I've just drawn is going to represent the displacement. How am I going to go ahead and find the length of that line? Or how am I going to go ahead and find the displacement? What mathematical skills have you learned in the past that are going to help you tackle that? The Pythagorean theorem. A squared plus B squared equals C squared. And this is why I made the question as straight lines as I could, because I can't assume that we have anything beyond that. That's a right triangle. So I want to find the length of this line. So I want to find what I'm looking for is the length of what is that side in this triangle. It's the hypotenuse. So in the Pythagorean theorem, this is side C. So then to find that length, we're going to plug in, doesn't matter what A and B are, the other two sides. So it's going to be 150 squared plus 300 squared is going to equal C squared. So then your displacement then is just going to equal the square root of 150 squared plus 300 squared. What is that value?
112,500.
And take the square root. 335 point what? Are you rounding it off there, or does it actually end at 4.1? Okay, cool. That works for me. So now we've got our magnitude. That's the size of the displacement. We traveled 450 meters. That's the distance we traveled, but we are actually only 335.41 meters from where we started. That's our displacement, or the magnitude of the displacement. And now we need a direction to go along with it. When you start to deal with two dimensions, and even the kind of what we were talking about yesterday when I was when Brad was telling us where he was, I started to get really picky because he said northeast, but Brad wasn't northeast. Other people were northeast. Brad was actually north by northeast. And so let's get really picky. How do we figure out what the direction is going to be from where we started to where we ended? Well, let's put in some values here because this is just a compass, effectively. How good are your guys' directions? According to this picture and the actual world out there, what is this direction? Left and rights don't count.
Where are you saying?
I want specifically this one here. On the page, it's to the left. But if I pulled up Google Maps, don't we pull up Google Maps? Which way is 7-Eleven from here? That we said yesterday, that way is north. So according to this diagram, this down here, the down on my page, is actually north in the real world. Sorry? It runs east-west. Which is it? Is it east or is it west? If this is north, then that way is west. So this is going to be east. That's going to be south. And that's going to be west. So northeast, when we say northeast, it's not, again, it's going to bug you all semester, but I'm going to say it again and again and again. When we say northeast, mathematically speaking, we mean that this angle here is 45 degrees.
North-northeast.
If it's north-northeast, it's halfway, what's half of 45? 22.5? Like, those words actually have numeric meaning. And so what we're going to go do is we're actually going to go find the value of this angle so that we can figure out what our direction actually is for the displacement. If I have a right angle triangle, how are we going to go ahead and find the direction? How can I find what an angle is in a right angle triangle? It's going to use some combination of SOHCAHTOA. So I want pink. We're going to have to use SOHCAHTOA, which I reviewed with you briefly in the first little unit. And when we use SOHCAHTOA, especially in physics, where we're actually like finding displacements and things as much as possible, when you're using trig ratios, you actually only want to use information that's already been provided to you. So like the 150 here and the 300 here. If I'm using that angle and I want to use these two sides, which trig ratio is going to be useful here? It's going to be tan, because the 150 is opposite, the 300 is adjacent. So then to figure out what this angle is, I'm going to call it theta for now because I don't know what it is. That's the variable we use to represent an unknown angle. And so the tan of angle theta is going to equal opposite side, so the 150, divided by the adjacent side, 300. And now I want to figure out what that angle is. So I'm not going to use tan. I'm going to use the opposite operation of tan to get that angle by itself. The opposite operation of tan is tan inverse. So your angle theta is going to equal the tan inverse of 150 over 300. What is that value? Sorry? What's the next decimal place? So then it would round to 26.6. It's not that I don't believe you, but I've been teaching physics for a long time and students sometimes don't know how to round. So I believe that you round properly now, Ray Reed. I'll never ask you again. So theta is 26.6 degrees, okay? And so then how we would quote this, when asked for the displacement, we would say, okay, let's put it all together. Our displacement, or the change in the position, has a magnitude and a direction. The magnitude Ray Reed gave us is going to be 335.41 meters. That's the magnitude. And now I want to know which way. Well, the way we quote it is we say, especially when we're dealing with angles, we say from one of the cardinal directions. So either from north, from east, from south, or from west, I have measured this angle. So the way we did this, the way I drew it is I measured from north out 26.6 degrees. And so then the way we write that is we would say that we are 335.41 meters, 26.6 degrees east of north. Because from this cardinal direction north, our angle opens east. So this is how we would write our displacement vector with its magnitude and its direction. We are going to do very little in 2 dimensions in Physics 11. Most of the 2-dimensional stuff gets saved for Physics 12. We'll learn how to deal with vectors more completely next year. But this is kind of your introduction to it. Comments, questions, concerns about displacement in 2 dimensions. Okay, cool. Then flip the page. One more example, and then we're going to make it more interesting. Here's a graph. This is the graph that represents the displacement of a swimmer. And reading graphs is something that physics students, seems to be the bane of physics students. And that's okay, let's play with it. Because this isn't actually a 2-dimensional picture. If we stop and think about what it means and how the graph is labeled, I have a position east and west on the y-axis, and the x-axis is just time. So the thing that lots of students want to do is, if you're looking at this graph, what I see students do all the time is I see them say, okay, they lay this graph in their head over the picture of a pool, and they see someone swimming in 2 dimensions up and down a pool. And that's not what's happening here. What this graph is saying is that as time is progressing, our swimmer's actually going east and west only. So if I'm going to demonstrate what this graph would look like, let's call this chair 0. And our swimmer starts where? What is the initial position of our swimmer on the graph? 10 to the right. 10? Well, that's not to the right. It's 10 east. Well, east is this way, but that's north. So here I am 10 meters to the east. As time progresses, what does the swimmer do? Starts moving west. Here I am at 0. That should have taken, if I'm mimicking the swimmer exactly, that should have taken me how long? 9-ish seconds. That's right. I'm at position 0. I decided that this chair was 0 at the 9-ish second mark. He didn't stop there, though. He kept going. At the 12-second mark, he's over here 4 meters. That's not quite 4 meters, but 4 meters west of the chair. And then what does the swimmer do? Just heads back the other way he came from. So this is a one-dimensional problem. Swimmer's just going maybe just a lap. And for some reason, 0 is in the middle of the lane. Right? But that's the data. This graph represents one-dimensional motion for, and again, in this case, a swimmer. So we can answer some of these questions, and based on what you guys just said, this is going to be fairly straightforward for most of you. Where is the swimmer at 4 seconds? Well, to figure that out, we're going to go to the 4-second mark, and we just go up to the line. Sorry? 8 east. We've got our value, we've got our units, and then we've got our direction. 8 meters east. East of what? Well, east of whatever 0 is. I don't know what's at 0. I don't know why 0 is in the middle. But 8 meters east of the origin. At 6 seconds, the swimmer is where? Six meters east. At 10 seconds, the swimmer is where? 2 meters west. Good. 10 seconds, we go down to the line, and then we go over to our axes. 12 seconds, our swimmer is where? Sorry? 4 meters west. I'm going to stop writing west. I'm just going to write W. And then at 20 seconds, our swimmer is back where? Oh, sorry. Yeah. "20 seconds is 8 east. So 8 meters E. So those are positions. Now we can start to calculate displacements. Remember, displacement is just a change in position. So it is the change in position, which is the final position minus the initial position. So from 6 seconds to 10 seconds, what is the displacement of the swimmer? We've got these values here. We've got at 6 seconds, they were 6 meters east. At 10 seconds, they were 2 meters west. So if we're going to use this change in position is equal to your final value minus your initial value, what's the final value over this time interval? Which of these represents the final time for this time interval? The 10 seconds. So what was the position at 10 seconds? 2 meters west. And when you actually go ahead and do math with this stuff, we have to take east and west and turn it into positives and negatives. On our graph, west was negative. So then at 10 seconds, the position is going to be negative 2 meters is our final position over this chunk of time. We're going to take away the initial position. At 6 seconds, they were 6 meters east, and on the graph, east was positive. So it's going to be negative 2 minus positive 6. So what meters? So then what's the displacement of our swimmer in the 6 second to 10 second time interval? Well, negative 2 minus 6 isn't going to be 8. It's going to be negative 8. And then we can take that and go back and turn that back into a meaningful direction. Negative 8 means 8 meters what? West. You got to be careful how you start subtracting these things now, because the east and westness is going to start messing you up. Thank you, Emma, for demonstrating that. I really do appreciate that. It had to be someone. So then the next one, from the 12-second mark to the 18-second mark, we don't have the time value for 18, we have the time value for 20. But we can go ahead and find it. The final position is going to be the 18-second mark. At 18 seconds, what's the position of our swimmer? 4 east, okay? So our change in position here, the final value is going to be 4 meters. East is positive, so I'm just going to leave it as positive 4 meters. We're going to take away the initial position. What was the initial position of our swimmer during this time interval? -4, or 4 meters west. Good. So what's 4 minus -4? +8. So then our swimmer was displaced 8 meters east. Which, if you actually go ahead and look at the graph, makes a lot of sense, right? 12 seconds, our swimmer's down here. At 18 seconds, our swimmer's up here. We can just kind of count it. 1, 2, 3, 4, 5, 6, 7, 8. Our swimmer swam east 8 meters, which, if you look at the graph, is easy to see. Going ahead and actually making sure the math makes sense is another step, yeah. So then the final displacement of the swimmer is what? 0, Kai says. Why, Kai? Because the swimmer ends where they started. What is the total distance traveled by the swimmer? Sorry, Emma, louder. 20. It's 20 something. It's not 22. It's not 24. They start at 10 east, they end at 4 west. It's going to be 28. Let's go back and look at the graph. They started at 10 meters east. They ended at 4 meters west. So this is going to be 10, 11, 12, 13, 14 meters out. And then they turn around and went back 14 meters. 14 meters plus 14 meters, 28 meters. Thank you, Colden. Distances only add, displacements do not. Cool, flip the page. Let's make it more interesting. When you change your position over a particular length of time, now we can start measuring something called speed and velocity, because that's all speed and velocity are. Speed is how long did it take you to go how far, and velocity is how long did it take you to go how far, which way. That's the only difference. Speed is, the way we define speed, it is equal to how far you traveled divided by how long it took you to travel. Those concepts are distance and time. Speed is equal to your distance divided by your time. And so because speed is dependent on distance, and distance is a scalar, speed then is also a scalar. Speed depends on 2 scalar quantities, so itself must then also be a scalar. And speed is given by what letter? The letter that makes the most sense for speed is, but it's not S. So speed's older brother is velocity, and the letter that makes the most sense for velocity is what? V. But since speed and velocity are related, and I said yesterday that velocity is just a speed plus the direction you travel, that means velocity must also be a vector. Speed's the scalar, velocity is the vector. just like distance and displacement have that same kind of relationship. And so if velocity is a vector given by the letter v, what needs to be added to this symbol to denote that it's a vector? All vectors have what piece added to their symbol? An arrow above them. But you're right. So velocity is v with the arrow above it. So then speed is v without the arrow. Speed's the scalar, velocity is the vector. So then if speed is distance over time, if you had to guess, velocity is going to be what? Sorry? We didn't do delta distance. It's close. You're very close, Yuli. It's the language that's attacking you. The equivalent, the vector equivalent to distance is what? Yuli was trying to say the change in position. Change in position is called? Someone say it louder. Displacement. Velocity is displacement over time. So we condense this. We're going to create our, not create, but I'm going to provide you with your first set of formulas found on the top back side of your formula sheet. Speed is distance over time. So then it's going to be written like this. V equals d over t. V is speed, d is distance, t is time. So then your velocity is going to be v with your arrow, the vector, velocity, is equal to your displacement, and as Yuli said, displacement is just your change in your position divided by the time. The formulas look very similar, but those arrows there change the meaning pretty wildly. And in fact, to add a layer of confusion, your formula sheet actually goes ahead and just drops the delta and assumes you understand that your change in your velocity is equal to your displacement over time, and it's going to write it like that. It's going to drop the delta. As soon as we formalize some notation, now we start to get sloppy with it, and that's just kind of how physics is. We get a little bit sloppy, and then we say, but you know that it's actually supposed to be this way. So let's go ahead and talk about this. A person travels west for an hour, travels 90 kilometers. What's the speed and displacement? I don't want speed and displacement. I want speed and velocity. So I'm going to put a dotted line here down the middle, and we're going to find both. Here is how it's going to feel painful to start, but when things get more complicated, having a framework to approach these kinds of questions is very, very useful. What I want you to do is write out the framework for this is to write out everything we know. Given the information in the problem, what do we know? It's one sentence. What do we know about the person and their travels? Okay, so the time taken is 1 hour. And what else do we know? The distance. "90 kilometers. And we want to know their speed. Well, speed is just v, no arrow. And we've got a formula for speed. Speed is just your distance traveled divided by the time taken. I want to see you write out the formula, and then we're just going to plug in some simple values. It's 90 over 1. But let's plug in those units too. 90 kilometers divided by 1 hour means our speed is 90 kilometers per hour. Velocity is going to be the exact same setup with one difference. The time is still 1 hour. What's the displacement now? Almost. 90 west. Displacement has to have the direction. So then the velocity now is what we're looking for. The equation is going to be very similar. Velocity is equal to displacement over time. The displacement is 90 kilometers west divided by the 1 hour. So then the velocity of our person is 90 kilometers per hour west. And if the direction doesn't change, speed and velocity are going to be the same. What happens if we change the direction? Let's make it more interesting. Example 2. A runner travels around a 400-meter track twice, returning to their starting position in 5 minutes. We want to find speed and velocity. So let's draw it, shall we? Here's the track. It's a circle or oval. And we're told that track is how long? It's 400 meters. Means you do the loop once, you will have traveled 400 meters. This person, here they are at the starting line, goes around how many times? Twice. So 1 loop, 2 loops, back to where they started. So let's find their speed and velocity. I'm going to draw my dotted line down over here just to break up the space so I can have it work it out. And we're going to write out what we know. If I'm looking for speed, I need a time, I need a distance, and I want to find the speed. What's the time? 5 minutes. But we don't like minutes. Time should be given in what units? Time. Sorry? Hours or seconds? Does it make more sense to convert the 5 minutes into a number of hours or to a number of seconds? Okay, cool. So if I'm going to, let's convert that. 5 minutes using our factor label method means I'm going to have to multiply it by what? 60 what? Per. I want to get rid of the minutes, so the minutes are going to go down in the bottom. I want seconds, so seconds are going to go up top. So this is going to be 60 seconds per 1 minute. The time then is what? 300 seconds. The distance traveled is what? They went around a 400-meter track twice, so that's 800 meters. So then the speed is just going to be the distance traveled divided by the time it took. The distance traveled is 800 meters. The time taken is 300 seconds. So then the speed is what? What is that value? You could theoretically do that in your head. Those zeros are going to cancel. Effectively, this is just 8/3. What'd you get? 2.6 repeating. So I'm going to round that to 2.67. And the units of that are going to be meters per second because the distance was in meters and the time was in seconds. This is how I want you to approach these kinds of questions. It's going to feel really stupid to start because, again, this is not an overly complex formula. But things are going to get bigger, things are going to get more gross, and the more you can put on the page, the less you have to carry around in your head. Basically, you're cognitively offloading is what I want to encourage you to do. The more you can get out of your head, the less you have to carry around, the better you will think about what you actually need to do. So the speed then is 2.67 meters per second. What's the velocity? Kai is suggesting that the velocity is 0. Why, Kai, do you want to say that the velocity is 0?
Displacement is 0.
Because displacement is 0. Displacement is 0 because the person started and ended in the same spot. So then the velocity is 0. Even though they ran 800 meters, Velocity is displacement divided by time. Your displacement is 0, and so the velocity is 0 as well. As soon as direction starts to change, that's what happened here. This person was turning around the track. As soon as you change direction, things get weird. Let's do one more. Here we go. A person travels north for 50 meters, then south for 30 meters. This takes 240 seconds. So let's draw this. Let's assume north is up the page, even though we know it's behind me. Here's our person. They go north, 50 meters north. They turn around, go 30 meters south. Let's write it all out. We want to find velocity, we want to find speed. Let's draw the dotted line down the page. Do them both. Let's do speed first. V equals, I don't know. I know a distance. What is the distance traveled by our person? 80 meters. Distances only ever add. And the time it took them to do that was 240 seconds. So if I want to find the speed, speed is just distance divided by time. Distance is 80 meters, time is 240 seconds. And so we're going to get a speed of, that's just 8 over 24, which if I reduce that fraction is just going to be 1 over 3. So that's going to be, I'll round that to 0.33 meters per second. If you want to punch that into a calculator, you can, but that's going to be the value. Velocity is going to be what? Velocity is dependent on displacement and time. Time is the same. Time does not change, but what is the displacement of our person now? The displacement of our person is just this green line. If they go 50 north and then 30 south, this distance is, Emma, you said 20. But displacement is a vector, needs a direction. That's going to be 20 meters north. So then this value is going to be our displacement. They were displaced 20 meters north. Sometimes we use square brackets around the direction if we're just using the letter. So then our velocity is going to be the displacement divided by the time. The displacement is 20 meters north divided by the 240 seconds. So the velocity is going to be what? 1 over 12, yeah. Which is, what is a decimal? Fractional values are useless in physics. A math teacher will never say that to you. A physics teacher always wants decimals. Because decimals make sense. A decimal meter is a centimeter. So then what's the, what is 1/12? What's a decimal? 0.083 meters per second north. And decimals, like I said, decimals actually make sense conceptually here. 0.08 meters is 8 centimeters. So effectively what's happening here is in the time it takes someone to do this, out, wall, we come back and we end right here. In the time it took me to do that, someone else could have just done this. I'm going out, I'm coming back, and we're going to meet at the same spot here in the middle. The velocity is 8 centimeters per second that way. The other person went 30 centimeters per second over the whole trip. The difference between speed and velocity. Questions, comments, concerns? Cool, then I'm done. Here's what I want you to do for the remainder of class and homework this weekend. I have provided you a little map. I cannot take credit for this. I found this map. I like the map. Below is a map of a happy country that lies within the subconscious of a crazy physicist. When they feel stressed out or sad, they go to this country. I don't know why they did this, but they do. And ponder kinematics problems as they travel from one happy town to the next. It makes them happy. It will make you happy too. Here's what I want you to do. There are 6 cities there: Zorkbaum, Fizzlestein, Quatsoff, Glurknoid, Stropfberg, and Rasissasa. The scale on this map is that 1 centimeter is equal to 10 kilometers. And these lines represent the roads, the paths taken between these cities. Perhaps there's mountains and lakes in there, I don't know. The road distances are listed here. What I want you to do for these 5 trips, a trip from Fizzlestein to Rasissa, traveling through Quatsoff and Stropfberg, that takes 3.5 hours. A separate trip from Stropfberg to Quatsoff to Glurknoid to Zorkbaum in 4.8 hours. A third trip from Rasissa to Stropfberg and back to Rasissa. And then Glurknoid to Fizzlestein through Zorkbaum. And Rasissa to Stropfberg to Quatsoff to Fizzlestein to Zorkbaum to Glurknoid and then back to Quatsoff in 23.4 hours. There's 5 separate trips there. What I want you to do for each trip is find the distance traveled, the displacement, the magnitude of the displacement means no direction. You do not have to pull out a protractor and find directions. And then I want the magnitude of the average velocity. Again, the reason I say magnitude here is because we don't have directions for displacement, so you're not going to have directions for velocities. Displacement is the actual path traveled. Displacement is the straight line distance between these locations. Initial position to final, or final position to initial position. So you're going to need a ruler that actually has centimeters on it. If you'd like to borrow one from me for the weekend, you're welcome to do that. For the remainder of class, and then over the weekend, this is what I would like you to do. I want distances, displacements, speeds, and velocities for these 5 paths. I have provided you with some blank paper to work with. You can do it all on here. That is your task. If you'd like to work together, you're welcome to do that too. On your mark, get set, giver. Why do you need a ruler? Because displacements are straight line distances. So you're like, for example, in the first one, guys, so there's been a question, why do we need a ruler? Here's why you need a ruler. Because if you want to find the displacement for the first path, from Fizzlestein to Rasissa through Quatsoff and Stropfberg, if we want to do the distance, we're going to start in Fizzlestein, we're going to Rasissa, but we go through Quatsoff and we go through Stropfberg, and we end in Rasissa. The distance is going to be the sum of these roads, 1, 2, 3, which are given to you down here. You just have to find the right 3 and add them up. Displacement is the straight line distance and direction. So you're actually going to need to pull out a ruler, measure the distance from where you started to where you ended. This will be the displacement. 1 centimeter on the ruler is equivalent to 10 kilometers in this country. So I don't have a ruler. Do I have a ruler that's marked? I don't have a ruler that's marked. Let us say hypothetically, actually I know what the value is. If I measure this from here to here, from Fizzlestein to Rasissa, that is, looks like about 8 centimeters on my crappy ruler. Fizzlestein to Rasissa, 8 centimeters. Well, 1 centimeter is 10 kilometers, so that's going to be a distance of what? Or sorry, a displacement of 80 kilometers. That's why you're going to need a ruler. Displacements will require straight line distances. There you go. On your mark, get set, giver. May the force be with y'all. You need to borrow a ruler from me over the weekend? Please bring it back. All I ask. You need a ruler that actually does measure. Not just the ones that are small. There we go. This guy, the first one is Fizzlestein to Rassissa. Force, that should be 84 kilometers. Number 2 is Strasbourg, which is Zorba. 7.6. It's going to be 76. Strasbourg. Glorknoid to Fizzlestein. It's going to be 6.9. 69. And the last one is Rassissa to Klotzau. 4.8, so that's going to be 48. Number 2. 76 divided by 15.83. Okay, have a good weekend. This is your homework. We'll go over it first thing Monday. If you need to borrow a ruler, please bring it back. Well, go ahead and then please bring it back. 9.86. 48 divided by. Yes.
Can you just write what you want us to do?
This.
Well, like, what did you want us to do with it?
I want you to find the distance, the displacement, the speed, and the velocity for each of these paths. Boom.
Is it raining?
It is. Looks like it is. Yeah, it's raining. Yeah, Steeler Kai.
How is this on the table for the weekend?
Yeah, go for it.
Now I'm assuming your weekend plans have changed.
I don't know. I have no idea.
Some family things probably.
I have no idea. Maybe.
Crazy.
I have no idea. I mean, we were expecting it to happen this weekend.
Yeah, Someone brought a shaker press.
See you later, Raina.
Mr. Sabine. What's your name?
Raina.
Raina, okay. Yeah. Her first day here, she mean early that day.
Raina did?
Yeah, so I've always said hi to her. She's one of the first people she met that I never knew her name. Hey, buddy. All the best.
Yeah, thanks, man. See you later. Yeah, you too, man.